Hello my dear students, welcome to Deeksha, Karnataka, and you are watching your favorite series Brahmastra 2.0, and today I am going to discuss current electricity. This is a very important chapter for your PU board exam, and in Brahmastra series we are specifically focusing all the important questions for your PU2 preparations taken from your PYQ series, PYQs taken from your model question papers and from your question bank. So we are going to cover all the important questions from current electricity, and definitely if you watch this video till the end, then how many marks you can get? If you see according to your latest blueprint, you can get up to 13 marks from this chapter alone. Okay, and very important thing is that from this chapter you are going to get 1 mark question 1, small answer type question 2 marker 1, no 3 marker question from this chapter, but there are going to be 2 long answer type question from this chapter, and that means there will be at least 1 long answer type theory based question, derivations, and 1 numerical going to be coming from this chapter. So you are going to get 2 questions from this chapter, 1 long answer type theory question and 1 long answer type numerical question. So both will come from this chapter. That's why this is a very important chapter. Now let us see how many questions we are going to discuss in this session today. So 15 MCQs. We will also discuss fill in the blanks 5. Now this chapter may be not that important for fill in the blanks, but we are not sure if MCQ will come or fill in the blanks will come, but I am assuming maybe in case they give you 5 fill in the blanks, and obviously in your PU preparatory exam there is no such thing that they can give fill in the blanks from this chapter as well. So this I am going to discuss 15 MCQs, 5 fill in the blanks, 6 2 marker questions, 4 derivations, as well as 5 numerical questions in this session. So don't go anywhere. All the questions, all the important questions, as well as your model question paper questions and some important numerical questions I will discuss in this series, in this session. Sorry. Now let us start with a 1 marker session, 1 marker question. In case of metals with increase in temperature, so we are dealing with metals, okay, specifically metals, no other objects. The conductivity decreases. So you are increasing the temperature. So if you increase the temperature, then its conductivity decreases, it becomes a bad conductor. So correct answer is option A directly, but if you are interested you can read the other options. The average speed of conduction electrons decreases. Average speed of conduction electron always increases with increase in temperature. The resistivity increases. Okay, conductivity decreases, resistivity increases. The number of conduction electron increases, number of conduction electrons remain same. It does not depend on temperature, only their velocity can change. Okay, now let's move on to the next question. Identify the wrong statement from the following. So wrong statement means there are 3 of the statements are correct, only 1 is incorrect. That incorrect statement you have to identify. The drift speed acquired by free electrons per unit electric field is called mobility. This is the definition of mobility. Mobility means, if you remember, mobility is given by drift speed divided by electric field. So this is the definition of mobility. Drift speed acquired per unit electric field means unit electric field means this E is 1. So this is a correct statement. The conductivity of semiconductors decreases with increase in temperature. This is the wrong statement. Conductivity of semiconductors are not like metals. For semiconductors, its conductivity increases as you increase the temperature. So this is a wrong statement, and wrong statement means this is our correct answer for this question. The conductivity of conductors decreases with increase in temperature. This is a correct statement. Just we have discussed it in our previous question. Alloys are widely used in construction of standard resistors. Actually nichrome, manganese, their resistivity actually remains constant with temperature increase, almost constant. That's why it is used in standard resistance. Standard resistance means the resistance box that you use for experiments in your laboratory. Now let's move on. Before I go into any further, I just request you to go into our WhatsApp channel. The link of the WhatsApp channel is given in the description of this video. Also, to support us, please don't forget to subscribe to our channel and please hype this video so that it can reach more and more students like you who want to learn and study for your PU boards. Most of the contents in our channel are free. All content in our channel are free. There are some courses, paid courses, but all the content we are making in our channel will be absolutely free of cost. Also, please remember that the PDF of this lecture and all the lectures that we have done in our Brahmastra series will be exclusively shared in our WhatsApp channel. So don't forget to join the WhatsApp channel ASAP. Now, let's move on. A wire has a non-uniform cross-sectional area as shown in the figure. A steady current I flows through it. Which one of the following statement is correct? So let's see the figure once. So here we have a non-uniform cross-sectional conductor. So here we have an area A and here we have an area B. Okay, as you can see, the area B is much larger than area A. Okay, suppose the drift velocity here is VA, drift velocity here is VB. Current is steady, that means current is constant. Now we know that current is given by NEAVD. So current is constant, that means N constant, E constant, I constant. So only A and VD is changing over here. So from continuity equation we can say A into VA must be equals to B into VB. Okay, so higher the area, smaller will be drift speed. Smaller the area, higher should be drift speed. This is constant. That means here, as you can see, that area is smaller, that means drift speed will be bigger. Here area is bigger, that means drift speed will be smaller. Now let's see the options. The drift speed of electron is constant. Obviously not. As we can see, drift speed is changing with depending upon area. The drift speed of electron increases while moving from A to B. So now see, VA is definitely greater than VB, right? Why? Because area is smaller. Area smaller means drift speed will be bigger, right? So that means as you are moving from A to B, drift speed is actually decreasing, not increasing. The drift speed of electron decreases while moving from A to B. This is the correct statement. So we will mark this. The drift speed of electron varies randomly, which is obviously a random option, not correct answer. Now let's move on to the next question. The resistivity of metallic conductor dash with decrease in temperature. Okay, so the resistivity of metallic conductor dash with decrease in temperature. So resistivity, what happens if you decrease the temperature, resistivity also decreases because we are dealing with conductor. Okay, so resistivity decreases, not increase, not randomly increase, decrease. It does not happen like that. So if you are decreasing the temperature, resistivity will decrease, conductivity will increase. Kirchhoff's junction rule is a reflection of conservation of charge. Okay, conservation of charge. Kirchhoff's loop rule is a reflection of conservation of energy. Loop rule is energy, junction rule is charge. The value of internal resistance for an ideal cell. Ideal cell means ideally two options can be possible, either 0 or infinity. Now for ideal cell, the internal resistance should be 0. Next, when current flows through a conductor, its temperature increases, decreases, remains same, may increase or decrease. Now when current is flowing through a conductor specifically, the temperature will always increase because we know that Joule's heating law, H equals to I square RT. So as the current is flowing, heat is being developed from Joule's law, so that means conductors will heat up, that means its temperature will increase. SI unit of current density. Current density is given by J is equal to current divided by area. So its SI unit will be ampere per meter square. Okay, so correct answer is ampere per meter square, not ampere per meter cube, not ampere per meter, but ampere per meter square. the magnitude of the drift velocity per unit electric field. So magnitude of drift velocity per unit electric field, we have seen that in one of the previous question. It is called mobility. So mobility is given by drift velocity per unit electric field or drift velocity divided by electric field. Okay, so this is called mobility. Which of the following characteristics of electron determines the current in a conductor? Thermal velocity alone, drift velocity alone, both thermal and drift velocity, none of the above. Now just to remind you, current in a conductor is given by NEA VD. There is no thermal velocity component over here. That means current in a conductor depends only on drift velocity. No thermal velocity is involved over here. Okay, thermal velocity, current in a circuit is independent of the thermal velocity. Next question, a piece of metal is to be converted into a rod of highest resistance. Which of the following is the best choice for the length L and diameter D? So you know that resistance of a conductor is given by rho L upon A. Now what is A? A is area, which is given by pi r square, or it is given by pi d by 2 square or pi d square by 4. Okay, so from this we can say that resistance is directly proportional to length and resistance is inversely proportional to square of the diameter. Okay, if you put this, you will get it. Okay, so if you have any doubt, rho L by pi d square by 4 or 4 rho by pi L by d square. Now this is constant, so only it is proportional to L, it is proportional to 1 upon d square, or inversely proportional to square of d. Okay, so basically if you want to have highest resistance, the length should be highest and diameter should be smallest. That the combination we should look. So in the given combination, if you see that highest length is 2L and smallest diameter is d by 2, so this should be the option where you should get the maximum resistance. Okay. For highest resistance, for smallest resistance, length should be smaller and diameter should be maximum. This is smallest. Okay, from the given option, this should be smallest. Okay, if the same question is asked with the smallest resistance, in that case you have to remember that length should be smallest, diameter should be largest, so that resistance is smallest. Okay, from this option, highest length, smallest, diameter is the highest, because in the question it is mentioned highest. So now let's see question number 12. A steady current I is flowing through a conductor of uniform cross section. Which of the following is conserved? Conservation of momentum, conservation of current density vector, conservation of charges, conservation of energy. Now in case when a current is flowing in a conductor, always charges are conserved. That's why we say Kirchhoff's junction rule. Current is always involved with Kirchhoff's junction rule. That means charges are conserved. So option C is correct. Now next question, a wire of length L is stretched to double its length. So whenever a wire is stretched, okay, what happens is that whenever you are stretching the wire, okay, its length increases but its area decreases proportionally. Okay, so if length becomes 2L, so suppose this is L, this is A, then once the length becomes 2L, the area will be proportionally be halved. Okay, so when area length increases to 2L, area becomes half, and the resistance, new resistance, is actually N square R, where N is this factor. For this problem, this is N, so resistance will be 2 square R, that is 4R. So resistance will be 4 times. Okay, resistance of the wire will be quadrupled. Quadrupled means 4 times. Quad means 4. Okay, quadrupled means 4 times. Okay, so resistance will be quadrupled. Resistivity remains same. Okay, resistance becomes quadruple. Resistivity only depends on material as well as only temperature. Okay, now let's move on. Ohm's law is applicable to diode, transistor, electrolyte, conductor. Ohm's law is only applicable to conductor. These are non-ohmic conductors, so the Ohm's law is not applicable to them. as the temperature increases, the resistivity of metals increases and semiconductors decreases. So as the temperature increases, the resistivity of metals decreases and resistivity of metals increases and that of semiconductor decreases. So option A is correct. Okay, that means metals become poor conductor and semiconductors become better conductor. Resistivity decreasing means it is becoming a good conductor. So semiconductor is becoming a good conductor, whereas metals resistivity increases, that becomes a bad conductor. Okay, so all the MCQs are over. If you have any doubt regarding any MCQs, please mention that in the comment below. In a current carrying conductor, the net charge is dash. So in a current carrying conductor, the net charge is, if you see that, it is 0. Net charge of a conductor whenever it's carrying current is 0. So correct answer is 0. The magnitude of the drift velocity per unit electric field is called mobility. So correct answer is mobility. The SI unit of dash is ohm meter. So what is ohm meter? By the way, ohm meter is the resistivity. Okay, ohm meter is given by resistivity. So it is electric resistivity. From the option, it must be electric resistivity. Next, the resistivity of certain metals or alloys drops to 0 when they are cooled below a certain temperature. This phenomenon is known as superconductivity. So there are certain materials whose resistivity becomes 0, it becomes the perfect conductor, and that happens for superconductors, and this phenomenon is called superconductivity. The Kirchhoff's loop rule is based on conservation of energy. Okay, loop rule is based on energy, junction rule is based on charge. Now let's move on to the 2-marker section. Define the drift velocity and mobility of free electrons in conductors, or define mobility, mention is SI unit. So these are both common questions. Let's see. Drift velocity is given by the average velocity with which free electrons drift under the influence of an electric field is called drift velocity. Very important to remember, it is always happens when there is a electric field is involved. Now mobility, the mobility of free electrons is defined as the drift velocity of the electron per unit electric field applied. That means mobility is given by drift velocity divided by electric field, and its unit is the unit is very interesting, meter square second to the power minus 1, volt to the power minus 1, or meter per second Newton to the power of minus 1 coulomb. How to remember this, by the way? So we know that mobility is given by Vd by E. So mu is given by Vd by E. Now what is Vd? Vd is drift velocity or drift speed. So what is the unit of speed? Unit of speed is meter per second, and division is electric field. So what is the unit of electric field? Unit of electric field is volt per meter, or you can say Newton per coulomb. Any one unit is sufficient. So Newton per coulomb. So what is the unit of mobility? Unit of mobility will be meter, okay, second minus 1, this is minus 1, Newton to the power minus 1, because this is in the division, and coulomb. Coulomb was division of division, that means it becomes plus 1. Okay, so this is the common unit of drift velocity. Now let's move on. Mention 2 limitations of Ohm's law. Very common question. Ohm's law is applicable only if all the physical conditions remain same. Ohm's law is not applicable at very low and at very high temperature. Ohm's law is not applicable to non-ohmic devices like semiconductor devices, discharge tube, etc. Okay, so these are the 2 limitation. Any 2 you can write, but if this question comes as a 3 marker, I have given is 3. Anyway, from this chapter 3 marker question is not going to come, so any 2 you can remember. Now next, give any 2 differences between current and current density. So difference between current and current density: current is defined as the amount of flow of electric charge per unit time, whereas current density is the amount of current per unit area. Now unit of current is A, unit of current density is ampere per meter square. Name 2 factors on which the resistance of a metallic wire depends. Okay, so resistance is given by rho L by A. So it is directly proportional to length, that is R is proportional to L. Now do not write this only R proportional to L, you have to write it in, you are getting 2 marks, right, for just doing this. So please write it in a sentence. And inversely proportional to area. That means R is inversely proportional to area. Okay, so these are the 2 factors on which resistance of a wire depends. Next, name the mobile charge carriers in metals. Write the expression for mobility in terms of average collision time or relaxation time for charge carriers. Now this is a new question from your latest blueprint. Electrons are the mobile charge carriers in metals. We know that, not anything else, only electrons can carry electricity in a metal. Mobility in terms of relaxation time, tau is given by mu is equal to E tau by m. Okay, E tau by m. E is the charge of an electron, m is mass of the electron. Okay, so this is the common form. State and explain Ohm's law. Ohm's law, this is also generally did not came, but this is given in your new model paper, so it might come this year. So if temperature and other physical conditions remains the same, the current I through a conductor is directly proportional to the applied potential difference. V is proportional to I, or V is equals to R, V is equal to IR. The constant of proportionality R is called the resistance of the conductor. Okay, so this is the statement and this is the explanation. Now let's move on to the 5 marker derivation section. 2 cells of different EMFs and different internal resistances are connected in series. Derive the expression for effective EMF and effective internal resistance of the combination. This is one of the easiest derivation. Okay, among all the derivations that we are going to do, this is the easiest derivation. So here we have 2 cells, epsilon 1, epsilon 2, R1, R2, and we have an external resistance R. The current in the circuit, say I. So this is the original circuit. Now original circuit is we are not interested, we are trying to find the equivalent circuit. So that means equivalent circuit will have only one EMF source, only one internal resistance. External resistance will remains the same, R. Okay, so epsilon equivalent and R equivalent. Okay, so these are the combination that you have to be careful of. Current in the circuit should remains the same as it was in the previous case, that is I. Okay, now we will apply Kirchhoff's laws and we will see what is the relation. So current I is passing through all the resistors. Okay, they are all connected in series. That means all the resistors should have the same current, I. So we will apply Kirchhoff's laws in the original circuit. So this is say circuit number 1, this is say circuit number 2. Okay, so we are applying KVL in circuit number 1 and we are getting IR plus IR1 plus IR2 equals to epsilon 1 plus epsilon 2. Okay, Kirchhoff's law says that we take voltage drop across each and every resistors according to the direction of current. If they are going in the same direction, everything will be positive, plus, and if, in between if you are going in the opposite direction, then it will be negative. But here everything is in the same direction, that's why everything is positive, and that is equals to EMFs of 1 or 2 EMF, whatever is connected. Now if you see that both the EMF are connected, cells are connected such that they are sending current in the same direction, that means they will be simply be added, or IR equals to epsilon 1 plus epsilon 2 minus I into R1 plus R2. This is equation number 1. Okay, so this is our equation number 1. Now we will apply the same, applying KVL in circuit 2. So now we will apply KVL in our circuit number 2, and initially it will be same IR plus I into R equivalent equals to epsilon equivalent. Only one equivalent is there, so IR in this case will be epsilon equivalent minus IR equivalent. Okay, so now this is our equation number 2. So if you compare equation 1 and 2, our left hand side is same. On our right hand side we have something minus something, here also something minus something, and one of them has a term current involved in it and another one has only EMFs. So if you compare these two, so we can write comparing one and 2, we get epsilon equivalent must be equals to epsilon 1 plus epsilon 2, and R equivalent must be equals to R1 plus R2, right? So this must be equals to this and this must be equals to this, okay, because they are same equation. So from there we can compare and we can say this is the correct derivation. So easy derivation, not super long, not super difficult. So this is, if you do that, you will get full marks. Now next, obviously circuit diagram is compulsory in this derivation. Next, move on. Derive the expression for effective EMF and effective internal resistance of two cells of different EMFs and internal resistances connected in parallel. So here we have two cells connected in parallel. Epsilon 1 R1, epsilon 2 R2, and because they are connected in parallel, the equivalent resistance in question should be connected in parallel as well. This is the original circuit, say circuit number 1, and the equivalent circuit is given by only one. Equivalent circuit is always the same, okay, only one equivalent resistance, equivalent EMF, and the resistance R. Okay, so now what we will do, we will do the same thing, apply the KCL and KVL, but in this case if you notice, here we have I1, here we have I2, and the total current in the circuit is given by I1 plus I2, that is equals to I, say. So here in this case I1, I2 will be not there, only I current, that is the sum of these two current will be there. Okay, so first we will take the outer loop, okay, from in circuit in CKT1 there are two loops, okay, if you name it, it will be very good, A, B, C, D, E, F. So first we will take A, C, D, F. A, C, D, F, A. Okay, A, C, D, F, A. What we are getting? Current passing through this resistor is I1. Remember that whatever current is coming out of a cell, same current should always go back to the cell. So anything is directly attached to the cell, it will always get the same current whatever is associated with that cell particularly. So I1 R1 plus, because we are skipping this cell altogether, we are going to the resistance directly, we can write IR equals to epsilon 1. Okay, only one EMF is connected in this loop, okay, loop, and second we will apply the same thing in loop B, C, D, E, B. B, C, D, E, B. We will get the similar thing, I2 R2 plus IR, I capital R equals to epsilon 2. Now if you see these two equations, you will notice that we are trying to find the total current I1 and I2 If they are alone, we can calculate I. But because they are associated with this R1 and R2, we need to simplify them a little bit. So how to do that? We will divide each and every term with resistance R1. So we get I R by R1 equals to epsilon 1 by R1. Okay? Or, okay, let me leave it like that. Similarly, we can get here I2 plus IR by R2 equals to epsilon 2 by R2. Okay, so now this is our equation 1, this is our equation 2, and we will add them. So 1 plus 2. By doing 1 plus 2, what we are getting? I1 plus I2 plus IR is common. So IR is common, and we get 1 upon R1 plus 1 upon R2 equals to epsilon 1 by R1 plus epsilon 2 by R2. Okay, so this is our first step. Now what we will be doing? We will be trying to do what? We know that this is equals to I. So let me write that I plus IR 1 upon R1 plus 1 upon R2 equals to epsilon 1 by R1 plus epsilon 2 by R2, or IR equals to epsilon 1 by R1 plus epsilon 2 by R2 divided by 1 upon R1 plus 1 upon R2 minus I divided by 1 upon R1 plus 1 upon R2. So we have taken this I on the left hand side, and everything we have divided by this term, because we are, whenever you are trying to find the equivalent EMF and equivalent resistance, always you need to calculate is IR. Okay, now we will apply the same Kirchhoff's laws, KVL, in the equivalent circuit. So from circuit number 2, we can write IR plus IR equivalent equals to epsilon equivalent. Or, now this is our equation number 3, let me name it. So IR is equals to epsilon equivalent minus IR equivalent, and this is our equation number 4. So now if you compare the equation 3 and 4, we can see this is the independent term without I, and this is the term with I. So by comparing 3 and 4, what we can say that the equivalent EMF must be given by this entire term. So equivalent EMF is given by epsilon 1 by R1 plus epsilon 2 by R2 divided by 1 by R1 plus 1 by R2. Similarly, R equivalent is given by 1 by R equivalent is given by, because it is in division, so that's why 1 by R equivalent is given by 1 by R1 plus 1 by R2. So see here R is in multiplication, here R is in division. So that means you have to convert it into division by doing 1 by 1 by R. Okay, so 1 by R equivalent is this. Okay, so this is a slightly lengthy derivation, but not super difficult. If you practice it 2 to 3 times, you should be able to do it. Okay, practicing is the key for mastering this derivation. Okay, previous one was easy, this one is slightly tricky, because you need to remember the steps. If you forget it, you will not be able to do it. Now let's move on. Arrive at the balance condition of Wheatstone bridge using Kirchhoff's rules. So this is the most common, came in the previous years. Okay, but this year, particularly in 2026, this may not come. Be cautioned about this, because in 2024 it did not come, main exam, first exam. Okay, but it came in 2025. So 2026, there is a chance some other question might come, namely the parallel combination of cells, series combination of cells, or whatever we are going to do the next, that is taken from your model question paper. But again, remember that this year it may not come in the first exam. Okay, there is a possibility, 50-50 chance is there. Okay, so don't tell me that later on, but I am not saying this is not important. This is the most common question. Other questions have come and gone, but this question is always the charm. Okay, there is a galvanometer. So we will name A, B, C, D. This is our P, this is our Q, this is our R, this is our S. Wheatstone bridge. Wheatstone is the name of a person, and this is called bridge because this was used to measure unknown resistance. There was a gap there in S, so unknown resistance can be measured using that value. That's why it is called bridge. Okay, bridge means it's not the bridge that you cross. Okay, because there was a gap there and unknown resistances used to put between those two gaps, so it is said that resistances are bridging the gap, and that's why it is called a bridge. Okay, when I was a student, even this was as a part of our experiment as well. Nowadays it is not there. Okay, anyway, so now we have to see that what is the balanced condition of a Wheatstone bridge. The balanced condition of a Wheatstone bridge condition is, what is the balanced condition? Ig must be equals to 0. So balanced condition of a Wheatstone bridge is Ig, that is the galvanometer should not have any current passing through it. So the balanced condition means the current through this galvanometer must be 0. That means if current I1 is passing through this, at this junction no current passing through this means entire current I1 must also pass through this one as well. Similarly, if I2 current is passing in this direction, then the entire I2 current should also pass through this, because no current is being added or subtracted from G. So first you write this. What I am going to do is the smallest or shortest derivation of this condition. Okay. Now first we will take the loop A, B, D, A. So from loop A, B, D, A. So when you are using loop A, B, D, A, we see that how many resistances are there? I1 into P plus current through this is 0, so G into 0 plus, now when we are going from B, D, A, okay, AB in this direction, BD in this direction, DA is, when we are going from D to A, if you see that the current is going in this direction, but our loop is moving in a circular way. So this is a opposite direction of the current. That means it will no longer be plus, it will be a minus, and it will be minus I2 into R, and that is equals to 0, or I1P equals to I2R, or P by R equals to I2 by I1. This is our equation number 1. Now if you see that current through P is I1, current through R is I2. So P is in numerator on the left hand side, whereas I1 is in the denominator. Similarly, R is in the denominator, I2 is in the numerator. So that means it's a inverse relation. So because of that, we can write similarly from loop BCDB, we can write that Q by S. What is the current through Q? Current through Q is I1. And where is Q is located? Q is located in the top, so I1 must be in the bottom, and current through S is I2, S is in the bottom, so I2 must be in the top. Okay, so this is our equation number 2. Right, clear? That's how you can write similarly, because everything is similar. So comparing 1 and 2, comparing 1 and 2, P by R must be Q by S, both have same on the right hand side, so P by R must be equals to Q by S, or P upon Q equals to R upon S. This is the condition for balanced Wheatstone bridge. Very simple, very easy derivation. Okay, this is the smallest or shortest derivation. In your college, in your textbook, in your teachers, they will do a longer form of derivation, but this will also give you 5 marks. That will also give you 5 marks. If you can do it in a shorter way, why to do it in a longer way, right? That is my thing. Now let's move on to the numerical. One more derivation is there, sorry, one more derivation. This is also taken from your latest model paper. Assuming the expression for drift velocity, derive the expression for conductivity of a material. Sigma is equal to NE square tau by m, where symbols have their usual meaning. Now this question I have not seen in the first paper, but this question is very common in second and third paper. Previously also improvement exams used to be held. From last year onwards, they have legalize the improvement. There is no improvement or supplementary exam. They have directly made it. You can attempt as many times as you want. Previously it was only if you have failed in the first paper, you should be able to attend the second or third paper. Now this is no longer there. You can consider them as improvement. Even if you want, so you got 90, you want to get out, you can still attempt the second one. Previously it was not there, but as I mentioned, this question never came in the first paper, but in the second and third paper this is a very common question. Maybe this year they will give this as a first paper question, who knows. So let's see. The derivation is not difficult. Assuming the expression for drift velocity, derive the expression for conductivity of a material. Sigma equals to N square tau by m. So drift velocity means what? Drift velocity is given by I equals to NEA VD. That equation we will use. Okay, nothing else. NEA VD, the simplest equation. Okay, or I upon A equals to NEVD. We have taken this in on this side. Now what is I by A? I by A is called current density. So current density is NEVD. Now we know that alternate form of Ohm's law is J equals to sigma E, right? J equals to sigma E. So from Ohm's law we will put sigma E equals to NEVD. So if you remember, we are trying to find the sigma, that is conductivity. So sigma equals to NEVD by E. Now VD by E is drift velocity per unit electric field, that is, this is the term called mobility. So this is mobility, so NE mu. Okay, now if you have remembered the short answer questions, mobility was given by E tau by m. E tau by m. Okay, so we will put that over here. Sigma equals to NE into E tau by m, or NE square tau by m. So this is the derivation, this is the formula that we are trying to derive. Okay, so this is how we have done the derivation. Very easy derivation, nothing difficult. Only critical thing you have to remember this and this. So if you follow these steps, you can answer this derivation. The no complication is over here. You have to start with I is equal to NEA VD. From there divide by current, get the current density and do it. So this is an easy derivation. That's why it is given to the second and third paper, so that weaker student can also attempt, but they always practice this derivation, that Wheatstone bridge derivation, and it did not came, and many students failed again in the second paper as well. So you have to practice all the derivations so that you are prepared. Now let's move on to the numerical questions. A copper wire of length 50 cm and diameter 1 mm carries a current of 3 ampere. The number density of free electrons of copper is 8.5 into 10 to the power of 28 meter cube. Calculate the current density, drift velocity of free electron, and the time taken by the electrons to drift from one end to the wire of the other end. A similar question was there in the last year model paper. This is directly from your this year's model paper. Only current density was not asked, otherwise these two was asked, and the values was slightly different. Now this kind of questions is always required to use calculators. I have seen this trend in your PU exam. The questions are asked such a way that you have to use calculator to solve it, but I recommend you do not use the calculator for everything. Try to solve it as much as possible, then use the calculator. So we know that what is first task? First task is to calculate the current density. So what is current density? Current density, this is first part A. Current density is given by current divided by area. Now current is given over here 3 ampere. Area is not given. Instead diameter is given as 0.1 millimeter. So we have to calculate the area. So how to calculate the area? Area is given by pi r square or pi d by 2 square. This is the area of a circle. Your cross section of a conductor is a circle, so that's why we are using this formula. Now what is the value of pi? The value of pi is 3.141. Diameter is 1 millimeter. So 1 millimeter means 1 by 2 into 10 to the power of minus 3 meter. So don't forget to convert the unit. So main problem that student faces, the question is easy, they forget to change the unit. So every time you are solving it, you have to change the unit. Okay, so it will be 3.14 into 0.5 into 10 to the power of minus 3 square, or 3.14 into 5 into 10 to the power of minus 4 whole square. So I have taken this decimal and put it on the 10 to the powers value. So it will be 3.14 into 25 into 10 to the power of minus 8. Square was there, so we have broken the square. This will be 78. This will be 78, approximately 78.5 into 10 to the power of minus 8. Okay, you can use the calculator and calculate this value. So area we have calculated. Now it's time for us to calculate the current density. Current is 3 divided by 78.5 into 10 to the power of minus 8, which will be, I think, some 0.38. I'm think it is with 0.38 into 10 to the power of 8. Okay, or let me see, 338 into 10 to the power of 6. Okay, and unit will be ampere per meter square. Okay, so this by this 0.38 10 to the power of minus 8 goes up, and it will be 38.10 to the power of 6. You can use the calculator to calculate the exact value. So part 1 is done. Next is part B. Part B is drift velocity of the electron. So we know that current is given by NEAVD. So from there we will not use this, by the way, we will even simplify this, NEAVD, or VD equals to I upon A divided by NE. Okay, why I have taken I upon A separately? Because I upon A is our current density, so we will put the current density value directly and the value of NE directly. So let's see. So VD equals to, current density is 38, I think it will be 3.8. There is a mistake over here. This will be 038, 3.8. Okay, 3.8 into 10 to the power of 6. Okay. Because I am not using calculator, I am relying on my memory. Okay, it will be 3.8. So 3.8 into 10 to the power of 6 divided by number density of electron is given 8.5 into 10 to the power of 28 into charge of an electron 1.6 into 10 to the power of minus 19. You will get some value. We will see the value in a while. Now next is you have to calculate the time taken by the electrons to drift from one end to other end. So that is point C. So to time taken by the electron to drift from one end to other is given by time equals to the distance or the length of the wire divided by the drift speed. Okay, length of the wire is given by 50 centimeter, that is 50 into 10 to the power of minus 2 meters divided by drift speed. Okay, and if you calculate everything, you will get that this will be 2.8 into 10 to the power of minus 4 meter per second, and this will be coming out to be 1.8, approximately 1.8 into 10 to the power of 10 to the, this will be plus, sorry, this is plus 10 to the power of 3 second. Okay, okay, so this will be plus. So if you see that the time taken by the electron to reach from one end to another is very, very high. So this is the approach. First you calculate the area, next you calculate the current density, and using the current density you can calculate the drift speed. If current density is not asked, you have to calculate the area and directly put these values over here and calculate the drift speed, and then time taken. Time taken is length divided by drift speed. Okay, S is equal to Vt. So from there T equals to S by Vt. Now what is S over here? S is the because current is traveling from one end of the wire to other end, that means electron which starts here, it has to travel the entire length of the wire. So that is the distance traveled by the electron. Okay, understood? Formula based problem, nothing else, but calculation is you require a calculator. Now next, move on to the next question. Calculate the power dissipated in the 10 ohm resistor in the given circuit. This is also taken from your model question paper, circuit theory based question. You can solve it in two ways. One is a shortcut way that I am going to do in this lecture. There is a longer way. So in that case you have to calculate the current through each parts and then add them. So current, suppose the current through this is I1, current through this is I2, current through this is I3. Okay, then we can, from Kirchhoff's laws, we can say I2 is equals to I1 plus I3. Okay, and then you apply the KVL. Okay, KVL across this loop, KVL across this loop, and then you calculate I1, I2, I3, and we are trying to find the power through this 10 ohm resistance. So I2 you have to calculate. So once we calculate I2, I square R will be the power dissipated in this circuit. But here we will use a slightly different approach. This is same. Okay, this part is same, current part is same, but here all of them are connected in parallel, and 1 ohm means there is a 1 ohm in series. This is not a simple battery. Okay, so be careful about that. This is not a simple battery. There it has an internal resistance. Internal resistance is not shown in the circuit, but it is mentioned as a comma. That means this is the internal resistance which is in series with it. Now first of all, if you see that all of them are connected in parallel, so in parallel combination, the voltage across each of them must be same, and that one we will apply. Voltage across each of the components is same. So we say voltage across this one is V, voltage across this one is V, voltage across the resistance is also V. Okay, so now we will use our shortcut method. So first we will take this battery only. So what happens is that because they are all connected in parallel and we have taken the common voltage, we do not need to consider any loop. Okay, you can simply consider this part only. So if you consider this part, current through this is I1, terminal voltage is V, terminal voltage of a cell, that concept we are going to use. So what is the formula for terminal voltage of a battery? Terminal voltage of a battery is given by epsilon minus I R1, here I1 R1. Okay, first battery. So terminal voltage is V equals to epsilon minus IR. Here V is same, epsilon 1, I1, R1, they are different. Okay, so from there we can say that V for top battery, top cell. Okay, so from here we can say V equals to 2 minus I1 into 1. Okay, resistance is 1. Or from here we can say I1 is equals to 2 minus V. I1 equals to 2 minus V. Now what about I2? I2 is only the resistance and the voltage. That means V is equals to, for resistance, V is equal to current times resistance. That means current is given by V upon R. So that is equals to V. We do not know V. We have to, if we can calculate V, we should be able to solve this question. So V by 10. Okay, resistance is given, R equals to 10, so V by 10. Now for bottom cell, what about for bottom cell? Same principle, V equals to epsilon 2 minus I R2, I3 R2. Okay, so V equals to 4 minus 2I3. Okay, R2 here is 2. So from here we get I3 equals to V minus 4 by 2. Okay, so terminal voltages are calculated. Now from Kirchhoff's current law we know this is the case. Okay, so I2 must be equals to I1 plus I3. So we will put that in this equation. So V by 10 equals to 2 minus V plus V minus 4 by 2. So this is, from this equation we need to calculate V. Okay, now multiply everything by 10. If you multiply everything by 10, you will get V equals to 20 minus 20 V plus 5V, 4 5s are 20. Okay, so now let's take all the V's on our left hand side. We get V plus 20 V minus 5V equals to, so there is a small mistake I made. Here it will be V 2 minus V. Okay, this is correct. This is correct, 2 minus V. Here I made a mistake. Here it will be 2I3 equals to 4 minus V, or I3 equals to 4 minus V by 2. So that is the mistake. So let me correct that. So here it will be 4 minus V. Okay, so it will be, and one more mistake I made here. We are multiplying with 10 each and every quantity, so it will be 10 to the 5. So if you multiply 10, 5 cancels, only 5 is left, so plus 20 minus 5V. Okay, so what I have done, 4 minus V by 2 into 10. So 2 cancels, 5, 4 5s are 20 minus 5 V's are 5V. Okay, clear? That's what I have done over here. So now take everything on our left hand side. Here we have V plus 10V plus 5V equals to 40. Okay, so V so 15 plus 1, 16V equals to 40, or V equals to 40 by 16, that is 5 by 2, that is 2.5 volt. So V is calculated. Now this is, even though this might look long, actually this is the shortest way to solve it. I1, I2, if you apply KVL and KCL, this can be little tricky. So I have done that in my live class yesterday, so you can go and check that out. There I have solved it using normal method of Kirchhoff's current law and Kirchhoff's voltage law. Okay, so V is 2.5. 2.5. Now we can calculate the current. We are only interested in the current I2, that is the current through this 10 ohm resistor. Okay, so I2 equals to V by 10, that is 2.5 by 10, that is 0.25 ampere. Okay, so 0.25 ampere is the current. Now what is the power? Power is I square R, that is 0.25 whole square into 10, and it will be 0.625 watt. You can use the calculator and calculate it. Okay, correct answer is 0.625 watt. Now let's move on. Three resistors, 2 ohm, 3 ohm, 6 ohm, are combined in parallel. What is the total resistance of the combination? If this combination is connected to a battery of EMF 2 volt and negligible internal resistance, determine the equivalent resistance, current through each resistor, and the total current drawn from the battery is. So first of all, we have to calculate the equivalent resistance. Three resistors connected in parallel, so equivalent resistance is given by 1 upon 2 plus 1 upon 3 plus 1 upon 6, that is 6, 3 plus 2 plus 1, that is 6 by 6, that is equals to 1. So R equivalent is equals to 1 by 1, that is 1 ohm. So R equivalent is calculated. First part is done. Next part is calculate the current through each resistance. Now here we have three resistors connected in parallel. Okay, connected in parallel. So in parallel combination, the voltage across each resistor should be same as the battery. So suppose I1, I2 and I3. So current through each of them should be same. So what is the current voltage that we have applied here is 2 volt. So current through first resistor, this will be I1 equals to the voltage that you have applied divided by the resistance R1. Okay, R1, R2, R3. Okay, is equal to 2 equals to 3 equals to 6. Okay, so 2 by R1, that is 2 by 2, that is 1 ampere. I2 equals to 2 by R2, that is 2 by 3 ampere. You don't need to make it into a fraction. I3 equals to 2 by R3, that is 2 by 6 equals to 1/3 ampere. So these are all the three currents. So total current in the circuit is given by I1 plus I2 plus I3 equals to 1 plus 2/3 plus 1/3, that is 3 by 3. 1 plus 3 by 3. So this is 3 by 3, that is 1. That means 1 plus 1 is 2 ampere. So current through the circuit is 1 ampere. Now if they ask you what is the power through R3, power through R3 will be I square R. I is given by 1 by 9, R is 6, so 6 by 9. Okay, you can calculate the power through any component as well. So this is the standard problem, and answer is 1 ohm, 1 ampere, 2/3 ampere, 1/3 ampere and 2 ampere. Now next, For copper, the number density of electron is 8.5 into 10 to the power of 28 per meter cube, and resistivity is 1.7 into 10 to the power of minus 8 ohm meter. Calculate the conductivity of copper and relaxation time of free electrons in copper. Take the mass of electron is given by 9.1 into 10 to the power minus 31 kg, and E is 1.6 into 10 to the power of minus 19 coulomb. Okay, so resistivity is given. First of all, you have to calculate the conductivity. Conductivity is given by 1 upon resistivity. Okay, so conductivity will be 1 by 1.7 into 10 to the power of minus 8, or 10 to the power of 8 by 1.7. You can take this as 10 divided by 1.7 into 10 to the power of 7. Okay, so I have taken one 10. I have so many tens. I have 8 tens. I have taken one of them. Okay, and it will come out to be, I think, 5, 6 approximately. I am not sure. 6 into 10 to the power of 7. Okay, conductivity will be ohm, not ohm meter. Ohm to the power of minus 1, meter to the power of minus 1. Resistivity is ohm meter, so conductivity will be 1 by ohm, so ohm inverse, meter inverse. Be careful about the unit. Now what? Next we have to calculate the relaxation time. For relaxation time, we know that conductivity is given by N E square N E square tau divided by M. We did this derivation few hours ago, few minutes ago. So N is given in this question 8.5 into 10 to the power of 20. So this formula you have to remember. Even if you remember the derivations or not, the formula you have to remember. This question again from your model paper and question bank. I think this question is taken from your question bank. So 8.5 into 10 to the power of 28. E square means this square. 1.6 into 10 to the power of minus 19 whole square. Tau we are trying to calculate. So this value we have known, 6 into 10 to the power of 7. Exact value I will tell you in a while. Mass of electron is 9.1 into 10 to the power of minus 31. So you have to cross multiply, square this, but while squaring be careful. Here we have 10 to the power of minus 19 whole square. That means it will be 10 to the power of minus 38. This one will go up and become plus. So all the 10 to the power calculation you have to do properly, and you will see that this will be approximately, tau will be approximately 0.25 into 10 to the power of minus 13 seconds. Okay, so this is the answer, and I have taken this as 6, but it can be taken as 0.59. Okay, both are okay. 0.59 10 to the power of 8. I have taken it 6 into 10 to the power of 7. Okay, so even my guess was not that bad. Okay, so just you have to use the calculator to calculate these values. As I mentioned, in board exams, the data or values are given randomly. They don't care about whether it is solvable without calculator or not. Their main objective is to give the accurate values as much possible, and that's what they have done. Now, next question. The terminal potential difference of a cell connected to an external resistance 4 ohm is 2.4 volt. When the same cell is connected to an external resistance of 9 ohm, the new terminal potential difference becomes 2.7 volt. Find the EMF and internal resistance of the cell. So cell based questions are day by day coming common. Last year also they asked one question based on cell, parallel combination of cell, but this is a separate question again from your model question paper. What is the terminal voltage? Terminal voltage, always remember, is given by epsilon minus I into R. Okay, so in the first case, terminal voltage is given 2.4 when you are connecting to an external resistance of 4 ohm. Now what is V? By the way, V is given by I into R. Okay, so from combining these two relations, we can say IR equals to epsilon minus IR. Okay, so I should be equals to epsilon by R plus R. Okay, this is the easiest formula, but we are not we will not use this formula. What we will use something different. What different is from this relation we will calculate the current is given by V by R. Okay, so first case, so these are the all general formulas. First case, okay, voltage V1 is given by 2.4, resistance is given by 4 ohm. So what is the current in the circuit? Current in the circuit is given by voltage by resistance, which is 2.4 by 4, which is 0.6 ampere. Okay, so 0.6 ampere is the first stage current. Now we will come back to our common equation, this equation we will use. So V1 is again equals to epsilon minus I1 R. We do not know epsilon, we do not know R, right? So two variables, we need two equations to solve. So V1 is 2.4 and epsilon we do not know, I1 we have calculated 0.6, R value we do not know. Next case number, this is case number 1 by the way. Next we will use case number 2. So let me erase everything here and we will use case number 2. So what is case number 2? In second case, same battery is connected across 9 ohm and voltage is 0.27 volt. So what will be the second current? Second current will be the voltage divided by the resistance R2. Here it is R1. So V2 is 2.7 and R2 is 9. That means current is 0.3. So again we will use the same equation. 2.7 equals to epsilon minus 0.3 R. Okay, so now we have to eliminate one by one and solve it. So we will, this is our equation number 1, this is our equation number 2. So if we put this this equation over here, we can get 2.4 equals to epsilon minus 0.6 R. Now what we will be doing, we will be subtracting minus plus. So we get 2.7 minus 2.4 is 0.3 equals to 0 minus plus 0.6 minus 0.3, that means it will be plus 0.3 R. Be careful, the values are not complete, so you have to take the fraction. Okay, so 0.3 equals to 0.3 R, or R equals to 1 ohm. So R is now calculated. Now we will use any one of the equation. I am using this equation. So putting R equals to 1 ohm, we get 2.4 equals to epsilon minus 0.6, or epsilon equals to 2.4 plus 0.6, that is 3 volt. So 3 volt is the EMF and 1 ohm is the resistance. Clear? Not a difficult problem if you know how to solve it. Better than circuit diagram related questions. Okay, students started avoiding this chapter because of the circuit diagram related questions. That's why the board also decided that we may not give circuit diagram related questions from this chapter. Okay, so this is the end of this chapter, and if you like our series, please don't forget to like, share and subscribe. I will be back with a new lecture on the Tuesday. Till then, bye.